That's weird. Hi teams. This is Qian Wang from UC side. Today I'm going to present our work about the Qure. Is the usable and attack-resistant security framework for quantum emulators. And this is a collaborative work with Dr. Lin Tian from Physics Department, as well as Dr. Yuntao Liu from Lehigh University. So quantum emulators and simulators are used for prototyping the quantum algorithms for benchmarking and validating the quantum applications in the noisy intermediate quantum scale era. But as those emulators evolves, like showing these figures on the up top, you can see like it has becomes a more and more complex working flow. Like it will include the quantum circuits complication, the quantum emulators, quantum controllers, which is sending the real pulse signals to manipulate the quantum hardwares. So for each of the stage, it will have those potential noise attacks to tampering the system. As well as nowadays, we are trying to put in lots of works on the cloud in a shared base. So that will also introduce additional potential security attack surfaces to this quantum emulation workflow. So for this project, we first want to try to address the noise injection attack, which is different from the intrinsic noise generated by the quantum emulation system. So the first challenging is like we try to distinguish from the intrinsic noise, which we consider as a benign noise that exists in the quantum system, to those like the attackers can deliberately add the perturbations to this noise to generate some like harm outcome to the quantum emulations, like some kind of like hardware Trojan's attack. So that's our first purpose. By identifying those attacks, which has been applied for those quantum emulation framework, we'll try to protect and prevent those attacks to generate those to influence our quantum outcomes. Also we are trying to build a collaborative security operations center, we call it SOC here, to protect the quantum emulation process. So those will altogether guarantee the reliability of the scientific results, especially very important for this physicists who are studying the quantum phenomena, and also build the trust of a broader research community. So our work has been outcome from both usability and cybersecurity. For the usability solutions, we try to first find an end-to-end security validation framework for those quantum for this quantum emulation. So that will integrate in both compile time and runtime predictions for the quantum emulation process. And we want to build up a user-friendly set of software tool that will be benefit for those physicists who may not having those security or cybersecurity experts, but they need like to guarantee their scientific results are validated and validated and accurate. From the technical cybersecurity solutions, we first want to try. We first want to categorizing and characterizing those quantum noise attacks, and we want to using those characteristics to build a kind of like a classification or recognition terms that can be identifying those malicious noise injection to the quantum emulations. And the other is like we want to use in the quantum ASIC models as our attack test beds, which is the ASIC models is used a lot in the physics for emulate the quantum phenomenon. So that can bridge in both theoretical modeling with the real world cloud quantum platforms. For the benefits for the scientific infrastructure, for this work, it will provide like ensure the cloud quantum service that could be emulate platforms are secure, reliable, and trusted by the scientific users. And this one will also reduce the risks of adversarial noise, such as Trojan attacks, to crack in the quantum emulation outcomes. We admire there should be some challenges for those for this work. One thing is like the noise complexity. We will try to distinguish between the natural noise and the adversarial perturbations in the quantum emulation. So that may need some techniques to identify those different noise. And we know like since we now put everything on the cloud, so that's evolving some like commercial quantum platforms may limit the access to low-level error data needed for robust validation. We try to solving this by using like specific simulators to make up those like missing data from the cloud providers. And this work is the first to try to establish this first kind of series and tools for quantum emulator security. So we need to manage well from how we make this tool's usability and how to make it benefit for the quantum computing framework. So our results and the mission plans would be we want to first demonstrate the ability to detect and mitigate the adversarial attacks on quantum emulations with qualified improvements for the fidelity and the reliability. And we want to establish a collaborative security operations center with active partners from the quantum physicists and cybersecurity experts. And we would like to result in publication for attack datasets, benchmarks, and detection scripts on public accessible shared repos. So this project will start in 2026 January, and it will last 3 years, and it will led by UC Merced as collaboration from Lehigh University. We also have an unfunded collaboration from Kent State University, where the Dr. Jiang there, he's like the expertise in HPC for quantum simulations, and he is willing to use our tools in his system. Thank you for listening.
All right, excellent. Thank you. So, across the board, again, no requirement or anything for projects to collaborate, but we do think it is useful for you guys to see what the other teams are doing. And so all three of these, the projects so far seem to have some commonalities in terms of, attack data sets and benchmarks and that sort of stuff. And the more that can be widely shared and widely available, I think the better off the overall community is. So this is great stuff. Also excited to see a quantum sock. I think that's kind of an interesting. That was an intriguing aspect of the proposal to sort of say, hey, let's actually get together a security operations center or SOC for the quantum space. So that's pretty exciting. Yeah, great to see.